Good afternoon to everyone. Now I would like to call on stage Director of ISER Kolkata, Professor Sunil Kumar Khare, to say a few words about the ISER Kolkata and GYAN course 2025.
Am I audible now? Yeah, so hi everyone. It's not good, it's about the lunch time, so I am sorry that I kept you waiting. It's great pleasure for me to welcome Professor Kari Tapani Rizanen from University of Jyväskylä, Finland. Sorry for if I mispronounced. Actually, it's honor for this institution to host you, sir, and I know that our students are going to be enriched a lot by your presence. I know you are a person of eminence globally. About ISER Calcutta, we are a comparatively younger institution, 15 years of history. And we offer mostly flagship program of BSMS in all scientific disciplines, chemical sciences, biological sciences, earth sciences, mathematical sciences, and so on. Recently we are starting actually a new course in the computer and data sciences as well. But though we are young, we are smaller, but as far as research and our efforts are concerned, we are no lesser than anybody. We stand second in chemical sciences in this country after IIT Bangalore. So our students are proud for us. They are bringing laurels to us, and hopefully in coming years you will hear more about us. We have very strong faculty colleagues with various kind of expertise. So in this case, this GYAN course, which is a thought of the national leaders. So this is called Indian Global Initiative of Academic Network. This is normally funded to bring the global academic leaders here and to let them interact with the Indian scientific community and students to build capacity and accelerate the growth of research and innovation in our country. And this course actually encompasses supramolecular crystallography and soft-oxometalates, which is one of the primary, focus globally these days. So you are bringing lots of knowledge to us, Professor Rizanen, sir. You are very well known in the field of supramolecular chemistry and crystallography. I read about your CV, and I think crossing maybe 350 plus more research papers. Your work actually illuminates the complexity of molecular recognition and self-assembly, and your presence is an extraordinary opportunity for all of us. Alongside, I am very happy to introduce our own Professor Soumyajit Roy, who is pioneering on soft matter chemistry and soft oxalometalates, and he continues to inspire the students and faculty colleagues at Chemical Sciences in ISER Calcutta. Just for a note that it may have been about 22 years ago or so when he was a student like you in my class. Okay. But seeing him to grow like this, it's a pleasure and proud to me. This course stands at the confluence of structural chemistry, material science and molecular design, These are the areas that are central to modern chemical innovations and hold immense promise for transformative technologies in all spheres, be it energy, environment, and health. So it's very special moment for me to acknowledge and warmly welcome the student participants also. Actually, you are the flag bearer for us, and your presence and your interest in the course brings lots of happiness to us and confidence for the country's future in your hand. I welcome all the student participants who have joined across the country to us and hope your presence reflects your academic curiosity and your aspirations to engage at high level science. And I encourage you to absorb as much as you can from this course. This is 5-day course, and I have been told that about 50 students actually were given the registration. So those in 5 days will be very enriching experience for you. You carry lots of good things with you, lots of learning in supramolecular chemistry. In fact, life itself is a supramolecular chemistry. When I think in chemistry department, when you say supramolecular, you just think of the different way. But when I say supramolecular, I look at nucleic acid, protein, and lipids, and even carbohydrate. They are supramolecular. And more further, if they organize themselves within the cell, it becomes perfect example how nature has created life. That's a supramolecular thing. So you have to see in whole perspective. The biology also is supramolecular, but more complex than this. Hopefully someday we will be able to decipher to that level what you are doing today. So it's just not a course. It's a beginning of new mentorship, research collaborations, and perhaps your life-changing academic journey. Once again, it's a pleasure for me to thank distinguished professor and their generosity in sharing their time and expertise. Coming to India, not a good experience. Finland is a very good climate and cold. Maybe when he's here, it's getting hot. So, but hopefully our hospitality, I believe that Professor Haldar, thank you Professor Haldar, and Somajit will take care of you the best, and also for the participant. Hopefully you will get good food. It's not comfortable stay, but at least food will compensate it. So I wish you all very deeply enriching and rewarding experience. Thank you very much.
Thank you, Professor. Now to express our sincere appreciation to our esteemed guest, Professor Kari Lisanen, I would like to again invite our respected Director of ISER Kolkata, Professor Sunil Kumar Khare, to kindly perform the felicitations. Have a huge round of applause for him. And now please join me in welcoming Professor Roy to the stage to present a token of appreciation from Gyan Course and EFML family to Professor Sunil Kumar Khare and HOD of the department, Professor Devashish Haldar.
Normally I don't smile, but thank you very much.
Have a huge round of applause.
Your own professor and head of the division. He looks like a student, but
Sir, please already working.
So good afternoon everyone. We are having a bit of a technical glitch, so that's why we are delayed a little bit. So I request you to have patience and give us a couple of minutes time, and then I think we should be able to be back. Okay, so good afternoon everyone. I'm sorry for this delay, mild delay, because we had some technical glitch. So that's why we are delayed also a little bit by 10-15 minutes. So let us get started. So in the last class, what we had seen were in the standpoint or from the standpoint of SOMs, we had seen that an overview of SOMs, so how you can look at soft oxometalates and SOMs. Then we had come to the aspect of patterning with SOMs, how you can do patterning, and that we talked about microbubble lithography and so on. And today we will be talking about soft oxometalates in catalysis. And this is going quite nicely because, as you have seen in the morning class, Kari has been developing step by step with very basic concepts of crystallography, so which is really augmenting the aspect of these type of materials which are beyond this translational periodicity. And these are soft matter systems, and as we have said that with these soft matter systems you have lot of advantages over the systems that have certain rigidity. Now here in these type of systems we have the violation or not the necessity of translational periodicity. So you have these colloidal entities which are beyond the translational periodicity, which is quite nice in a way that you can form structures beyond translational periodicity as and when you want. So we will highlight only the aspects of catalysis, and as I mentioned to you earlier, so all this work has been possible because of this excellent group that we have at IICR Kolkata, and they are in the background as well with this program today. So now let us get started. So if you see, for example, this is active matter. So this is the matter that moves. It really moves in real time. And what I will show you today, unlike yesterday where we had, on Friday where we had seen that how you have this translational periodicity and how you had the motion of these particles under different conditions. Today I will show you the motion of these particles under optical field, and you will see that they move and you can control their motion with optical field. Patterning I have already talked about, so I am not going to talk about it today. So we will show you also some of these reactions which we have seen where we harvest the structural versatility of the soft oxometalates with these type of reactions. So, and I will go a little bit in depth with CO2 reduction systems, because these can tell you that how you can look at systems when the reactions are going on, and when you have the reaction going on, what is in the background. So instead of just focusing on the products and the yields, we will look at the mechanistic pathways for these type of CO2 reducing systems as well. So you can see, for example, this motion of the particle that was moving. So again, the basic framework, I'll repeat. So this is the basic framework which we follow. So we keep energy in the center, then you have the assembly and the disassembly. You can use it for partition, so we will not talk about partitioning. We will today talk about reaction and a bit about the motion, and then disassembly, disassembly, how it works. So last class I had talked about how these assembly, disassembly systems can be harvested for creating motion. So today you will see it's more driven by the phoretic effects and how you see the changes in the reaction systems and how you have this motion. So let us get started. This was a work that was done by Opabrita Mullik in my lab, and so what she did was quite fantastic. She started with titanium nanoparticles, so titanium dioxide nanoparticles, and then with this titanium dioxide she put on it MO7 type systems so that she gets titanium MO7 type SOX, and then she irradiated them for 6 hours and then put gold chloride and prepared finally this composite with titanium MO7 and gold. Now you will realize it. So these have three components. So the titanium is the photoactive component, MO7 is the redox component, and gold is augmenting in the reactivity component. So these are the three components which were built in the system and which does the reaction in there. So what happens there is the following. So you have this particle and you have the band edges. So these are like optical semiconductors, right? So that means they have a certain band gap, and in the band edges, two band edges, you can do two different types of reactions. On one edge, you can create basically with the harvesting of the light, you can differentiate the holes and the excitants, and we had referred to it in the last class. So the holes essentially split the water and then creates oxygen, and the electrons are then transmitted into the gold nanoparticle. Now because of this production of oxygen, there is a certain slip velocity that is created, meaning that there is a certain difference in the speed with which the particles are moving and the solvent, and then that leads to a slip velocity, and that in turn leads to the motion of these particles. And then on the other side you have the gold, which is then reducing this into this oxygen, into these oxo anions, and these oxygen anion radical then leads as a potent instrument for oxidizing any kind of organic pollutant. So the design was so that you have motion, and then with motion you have reaction, and with reaction you can develop or build in functionalities so that you can oxidize whatever you want. Now you know there are a lot of pollutants which you would like to decompose. So this is one system by which you can do that. So now about the characterization. So these type of materials, when you look for the characterization, you have to look them across in the electron microscopy, and here you have the electron microscopy together with the elemental analysis. So what happens is that you capture the radiation from the material, and by which you can find out the nature of the elements which are present. And this is how Opabrita was able to show that you have titanium, molybdenum and gold. And these were shown in this kind of systems, and then you see what happens, for example, when you have motion in these type of systems. So you have a beam of light that is coming across. So this is visible light, and with this visible light you have the creation of a hole and an electron, because in the valence band you have the hole. Now this hole will split water into oxygen and protons and the reducing equivalents. And then the electrons are then in the conduction band, and then you can have a coupled redox process that can go on in this bandage. in the conduction value. So what happens? MO7 or heptamolybdate has empty orbitals, and it is very easy to get MO7 reduced. And how you see that? Because if you reduce MO7, there is a change in color. And so what was happening was these electrons were injected into the MO7 and it was becoming colored like blue. And then with exposure of air, it comes back to the unreduced MO7. And on the other hand, with the gold and on the surface here, you could get this oxygen reduced into oxygen anion radical, which is then really like a potent like a bomb kind of a thing, which can break any organic molecules that it comes in its contact, right? So then what happens when you have the organic molecules which are in the contact, they are broken up, and they are broken up into their non-toxic components. And that's how you can degrade any kind of toxic materials over there in the reaction mixture. So the idea is very simple, that what Apabhita had and we had is that you take these type of nanoparticles in a bottle, right, and you add it to a polluted region, and then it moves, it cleans up the system, and then you can recover it. So that's more or less the idea of this active matter, which are quite potent for doing these type of systems. And I would also like to mention you here that these type of active matter systems were first pioneered by George Whitesides, who came up with two component systems where you have one component that was creating gas, and that would then in turn propel these type of nanomaterials. So, and in this case, what we are trying or what we are doing, we are taking three components together. We are taking the orophilic interactions, we are taking the oxometalate interaction, and we are taking, of course, the titanium's photoactive properties. So this is a combination of these three properties which we are using in getting these things done. And you can see, for example, the motion of these nanoparticles, as you can see them moving, and this is the direction of the motion which is shown with you. Now, it has a responsiveness with the intensity of the incident light. As you have more and more of this luminosity, then you have higher and higher displacements of these particles. So this is really like you control the intensity of the light and you see a change in their velocity. And that we can capture it with the diffusion coefficient, and you can capture these diffusion coefficients from directly live from the systems which are undergoing reaction under the microscope. Now later on we combined forces with Professor Ronojoy Adhikari, and then we were able to map the solvent force field, meaning that these particles are moving, but there is a turbulence in the surrounding solvent medium, and this turbulence will create some force field which will then propel your particles further. So this has been done really with ab initio type calculations, which is complex hydrodynamics, and Ronojoy is now in Cambridge University. So he and his student Abrojit Lashkar, so they did the analysis of the solvent medium. So you can indeed map exactly. And what we can also do, that we put some dyes and we could recreate these theoretical patterns which were present under the theoretical calculations. You could see them also with the reaction going on. Now, there are different kinds of systems which we then did. For example, we had SOMs in dithionite. Now, what happens with dithionite is, you know, dithionite can be very good reducing agent. So it reduces the SOMs and then it creates sulfur dioxide. Now the sulfur dioxide can then act as a propelling gas and move these particles. Similarly, you can have hydrazine. Now when you have hydrazine in your system, then with hydrazine you can create nitrogen, right? So you can basically reduce salts with hydrazine, and then the nitrogen is created, and this nitrogen then propels these type of systems under the field. Now these are chemical fuels by which the reaction is made, but you can do also use physical impetus or physical stimuli to do these type of reactions, which I have shown you earlier in the earlier part. Now these are essentially the mechanical power output, so the efficiency which you can calculate. If you are interested, you can have a look at this calculation, but I will skip it. So essentially what you can see that the efficiency is relatively high in both hydrazine and dicarbonate, and there is an optimum concentration where this efficiency is maximum. And this happens because beyond a certain concentration, you have the logging of the gaseous molecules on the active site surface. So that's why you cannot have motion anymore. So there is a drag that is created if too much of the reagent is present. So and on the other hand, if you have too less reagents or chemical fuels, then also the reaction is very less. So that would lead to low velocity nanomotors, micromotors. So that's why you need to see an optimum condition where you have this optimum velocity for these type of SOM-based active matter. Now I don't know if this works, but this is a video, for example, where you can see the light. Moment you switch on the light, this particle will start moving. Yeah, it works. So you can see it starts to move. And when you have these lights on, it has a directionality, and then when the light is off, it then immediately, almost instantaneously stops moving, and whatever motion you see is basically a diffusive motion. So it's not no motion anymore. So on one side you have the motion, then again you switch on the light, again it starts to move, again you switch off the light, again it stops. So we have done these lights on and off periodically so as to show that you can induce this motion. And in course of this motion, what we have also done are to decompose some organic pollutants like lacrimeters, like benzyl bromide and so on and so forth, which I will show you in the next slides. So basically, the moment you have the lights off, it immediately switches on. So that means you have a clear trigger by which you can do this type of controlled motion of these SOM-based nanoparticles. And it's what we called, or she called, a recyclable motion with on-off modes. And you have seen it, so 0 second, 10 second, 20 second, 30 second, like that you can do it. And what you see, the velocities, if you analyze the velocities, you will see a sharp and an immediate drop from the on mode to the off mode, then again on mode, then again off mode. So it's quite clear and quite obvious in these type of systems which have the immediate application. And this is the application. For example, the simple thing what we did was this methylene blue, which is a dye, right? It's a very simple application. So we have put methylene blue, and then this is the blue color, as you can see, and then immediately after 10 minutes or so, the color bleaches out, and you see after 20, 25 or half an hour, you can remove the dyes completely from your system. Now this is particularly important because you know that there are a lot of industrial grade paints and pigments which are left then in the moving water, right? So this is a very facile way by which you can put these type of active matter and you can decompose the toxic industrial waste containing these type of pigments or dyes directly over there. Not only did we do that, she also worked with the degradation of benzyl bromide. Benzyl bromide is a lacrimeter, meaning if you have a trace of benzyl bromide, you will have water in your eyes, so it's quite toxic. And what she did, she was able to show that you can in fact decompose benzyl bromide into benzyl alcohol, and benzyl alcohol is fine, and a little bit of benzaldehyde. So you have this situation where you have these moving particles with a particular specific use in mind that can translate or that can be translated to some nice new applications. Now the next thing what I will talk about you in the context of catalysis, this was done by Shruti Das, where we made or he made polyoxometalate, which was tungsten, copper, and phosphotungstate containing polyoxometalate. So it has a cap, as you can see, two caps, and a belt in between, and these are all crystal structures, and which are then connecting these two and forming a banana kind of a molecule, right? And what was observed is that with these ones, when you put them on reduced graphene oxides, if you put them on there, then there is a direct oxidation of water into oxygen. So this was quite a nice system, and we observed it, and the design was inspired by nature because we put in some manganese in there. So manganese is oxidizing in itself, so that's why we put in some manganese containing units over there, and then to oxidize these systems. So here, for example, you can see that this type of clusters, the oxygen only with the cluster, pure cluster itself. That means if you are doing a homogeneous catalysis, homogeneous water oxidation reaction, meaning you are only using the molecules for the water oxidation, then it's much less in activity. But when you make it a SOM with the graphene oxide type interface, then the activity increases. And here also you see a situation where the pH dependence is quite interesting. We see a maximum pH of around 7.5 where the oxidation is maximum. Now why you need 7.5? Because you know, if you look at the water oxidation reaction, the basic reaction is water going into oxygen plus, so if you have two molecules of water, then it goes into one molecule of oxygen, four equivalents of 4 protons and 4 electrons, right? That's the balanced reaction. So that means if you have a pH that is high in nature, then at high pH the protons are captured, right? And that pushes more and more the reaction equilibrium towards the right hand side. This is simple from the La Chatelier principle. So that's how at higher pH you will always have oxidation reaction. Water oxidation reaction is favored at higher pH, right? But why then you would ask that it should monotonically increase? Why is it decreasing then? It is decreasing at even higher pH because of the fact that you have decomposition of the oxometalates. Because oxometalates are mostly formed by condensation reaction, as I have talked to you in the last class, right? So you have metal, oxo, metal, this type of bonds, and if you have more and more of OH minus, then you will have the breaking up of the metal-oxo-metal linkage, because one hydroxide will come and it will attack one metal center, and then it will open up the MOM type of units. So that's why when you go beyond a certain pH with most of the polyoxometalates, it will decompose, and that would lead to the lesser and lesser efficiency. Of course, there are some polyoxometalates which are very, very stable, like for example the Preissler type anions, which have a ring-like structure. Those are very, very stable. Those are based on tungsten and so on. But anyway, so just to tell you that you have an optimum condition where you have the maximum oxygen, and then when you cross it over, you have a situation where oxygen production is very low. Now, we looked at it with detailed mechanistic, from detailed mechanistic aspects. And what we also found is that in addition to water oxidation reaction, this you can have a look at it, it's very standard. But what I would like to draw your attention on to is that if you have a condition where in addition to water oxidation reaction, you have water reduction or you have production of hydrogen. And that was quite interesting, but then at that time we were a bit late with the development. So we thought that we can do it in some other ways because we are creating reducing equivalents here, right? So photochemically we are oxidizing water and we are creating reducing equivalents. And that's how we moved on to these type of systems. So instead of focusing on water oxidation or pure water reduction, we moved on to this type of situation where we create these salts in excited states, and then when it comes back to the ground state, it will emit then the excited hole and an electron. Now the hole will then do the water oxidation as we have seen in the last part, right? And the reducing equivalents which you are generating then is injected to CO2, and this goes on to creation of formic acid. So which is quite nice, and at that time it was one of the earliest ones, and the turnover numbers were really, really high. It was around 1.4 million. So which is quite an efficient and a scalable system. But then later on, we thought, okay, it's fine, can we pinpoint it even more? So then it was work again of Shuntu. So what he did, he prepared this type of copper phosphotungstate type units. And these copper phosphotungstate type units were created because on one side you have phosphotungstate, which is oxidizing, and on the other side you have copper, which is reducing. So the idea was, can we do it modularly with compartments so that we have oxidation in one compartment and reduction in the other compartment, and we can show that there is a clear coupling between these oxidation and reduction components in these type of systems. And this is what we observed. So we did, of course, the control experiments and so on. So we ran it without CO2, we could not get any formic acid. And then here, for example, the idea was that here also we have the reaction going on at two bandages. So at one bandage you have the oxidation of water to oxygen, and in the other bandage you have reduction of carbon dioxide into formic acid. Now then what we did the reactions and monitored them with GCMS. We furthermore did isotopic leveling, meaning you look at the isotope, you take the isotope and you take an isotopic carbon dioxide so that you know that your formic acid is coming specifically from the carbon dioxide that you are injecting in your system, not from anything else or not from the decomposition of your compound. So then we put 13 CO2 and we could see a shift of around 3 wave numbers. So later on we looked also with the NMR spectroscopy that you have a difference in the formic acid that is produced from 13CO2 and the one that is produced from your 12CO2. So this is what was quite well studied and studied in quite some depths. Now we also looked at the kinetics of the system, and again, like yesterday we showed you, sorry not yesterday, on Friday we showed you that on the trails, or when you have the chips, catalytic chips, then on those chips, when you do the reaction, they follow heterogeneous kinetics. So likewise, here also, you see this type of sigmoidal curve, which is a result from the cooperativity, and then this is showing this sigmoidal type of behavior, meaning that you have a heterogenized media. So that means the SOMs as the heterogenizing media are the responsible active catalysts catalyzing these reactions. And then we looked at the catalyst loading, and we were able to see that with changing pH we can get these different types of catalyst loading. And here what we observed in formic acid, the pH dependence. Now here the pH dependence is quite interesting because you look at it and you get around 5.5 or around 6. Now why is that around 6? This is because you want to have a system where water oxidation happens at a higher pH, right? But you are doing carbon dioxide reduction, which is then favored at a lower pH because you are creating formic acid and you have to protonate the system. So that's why an optimum is observed, which we see neither too high pH, not too low pH, but somewhat near the neutral pH, but somewhat acidic pH. You see these type of systems. We then wanted to check that water oxidation is indeed coupled, meaning that you need water for these type of reactions. So then what Shuntu did, he did the reaction in dry solvent. So slowly reducing the water content, and then he was able to show that when you have dry solvents really, there is no CO2 reduction. So the reaction stops in these kind of systems, and you do not have any further reaction with these type of dry systems. Now we looked at the mechanism. So let us look at the mechanism. So what happens is we are starting with copper 2 tungstate. So this was the system, and here when the carbon dioxide comes in, we were able to see from the CV that you have a change as you have CO2 adsorbed on the surface, and then you shine light, you are able to see this excited state CO2 adsorbed species, which was slowly showing this decay in the excited state life. And then over here comes water, and the water is used up, and then over time you can see this intense band appearing, which is showing that you have a reduction of tungsten 6 to tungsten 5. Now this means that you will have an intervalence charge transfer, and that's why you will have color appearing in the oxometalate, and that's what we observe. Then this copper goes into, so this is still copper 2, then it goes to copper 0. So the copper is reduced, and this is the active species, we determined it, this is the active catalyst. So then this copper 0 reduces carbon dioxide to formic acid, and then copper 0 is reoxidized to copper 2. So in this way we were able to show very much in detail that how this modular 2 compartments of this molecule reacts even in a macroscopic condition, or microscopic conditions, because you have these extended forms of structures which are still showing the reaction. Now here I would also like to tell you that we have heterogenized media like these ones, which are useful for obtaining high turnover number, right? That means you can have more and more carbon dioxide converted into formic acid. But then the beauty of these systems is that we have information exactly on single molecular species, and these single molecular species are well characterized from crystallography, which you are learning in the morning. And then we have the exact structure. We do bond valence sum calculations from where we can calculate the valency of these metal centers, and then we are able to see that how the changes happens in the system from spectroscopy as well as from crystallography. So this is a little bit of application of the knowledge that you are developing in the morning. So these type of systems where you have applied crystallography to get into the application of these type of material systems, right? Now, what we also observed with these type of systems is that they are quite stable. So before and after reaction, it's quite fine. But over time, there is subtle degradation, and this degradation we believe is because of the mechanical reasons. We do not think it's because of the decomposition of the component, because we tried to analyze also partly the components which we recovered, but we realized we are losing some of the materials in course of our reactions. Now this was another work. This was done by Soumitra Bormon, who is now a professor, junior professor in JNCSR, Jordan University Center for Advanced Scientific Research in Bangalore. So he developed together with Shuntu these MOV9 type systems, And here also what I want to show you is exactly the same type of kinetics you observe. You observe heterogeneous kinetics, you observed oxidation, and you have these type of reduction reactions taking place. Now we change the system. This is to show you that it's quite general in principle, and then we use this MO368. This cluster was characterized crystallographically by Professor Akin-Miller's group in Bielefeld, and we used these systems, and again here we were able to use it for CO2 reduction in the same way. But here, for example, you can see that the HOMO and the LUMO, you have the two gaps, and you can do the reactions in that fashion. And because of a little bit of a time issue which we suffered at the beginning, so I will just maybe condense it a little bit. But what I want to tell you, here we use 13 CO2, and we could see the formic acid created with the 13 CO2 in there. We can see it from the NMR, and we can see it from the spec, from the mass spec. So we were able to see that formic acid created in the system with 13 CO2 labeled reagents is different from the 12 CO2 type systems which are there. So, and we were able to see with more reduced products, we were able to see we get also a little bit of formaldehyde, very little, but we still see formaldehyde. That means if your cluster is more reduced, then you have a tendency or you have a chance to get more reduced species. But on the other hand, what we also realized is because these oxometalates are intrinsically oxidizing in nature, we were not able to get more reduced products. So this was difficult for more reduced products that are in the system. So, and when we calculated per site turnover, what we observed is that the per site turnover is not that high, it's low. So that means because these are oxidizing, so per metal site turnover was around 6 or 7 units of molecules of carbon dioxide getting converted into formic acid, which is not bad, but it's not great either. And okay, so these are some of the basic reactions. I skip it like that, but what you can see, it's quite stable before reaction, after reaction, and so on. So this, then with this, we thought of doing an organic reaction, a simple organic reaction. So we started reducing carbon dioxide to formic acid, and together with that, we converted phenylacetylene to acidophene. And this was a very nice reaction that was done by my another PhD student. Her name is Joyita Loth. So she did this very nice reaction in the system, and she could show that from the retention times that indeed you have this conversion coupled with the formic acid production. Now when we realized that you have an intrinsic difficulty with the CO2 reduction with oxometalates because the per site turnovers are low, so we then joined hands with Professor Wolfgang Schiffberger, and this was the work I showed you. You remember I showed the picture also of Shauli Pal, who was the PhD student who is now in Czech Republic. So he then took these molecules, these are of oral molecules, and here the idea was with Wolfgang that he said we want to have an axial direction free. Now instead of making free, he put some triphenyl phosphine there. So then the triphenyl phosphine will break apart and will give way to carbon dioxide. So when you charge up your system in electrochemistry, so those were photochemistry, now this is electrochemistry. So in electrochemistry, when you put it on the electrode, you have this type of bond which is labile, it breaks apart and carbon dioxide comes in, and then you have the local pockets created where you have these carbon dioxide anions which will couple to give glyoxal, and this glyoxal then disproportionates to give you ethanol. So we were able to form more reduced species. So you see the basic thing is just looking at your systems in detail and then trying to think of ways, but of course looking at the system experimentally is very, very important, and that's what you need to do some nice simple reactions. And with this he was able to get this ethanol at around 47% of Faraday efficiency which is really quite high, as I have mentioned you. So this was at the time of production or at the time of publication, this was one of the highest value Faraday efficiency reported in the literature. And this is what happens. For example, you have stepwise reduction of cobalt followed, and you can see that it comes up and then it goes flat straight into the pocket of this porphyrin ring, and then there is a dissociation, and then this molecule goes away. You have free access of carbon dioxide from here to here. So this is the plane of the porphyrin ring, right? So we are showing it from side views, and then you have the CO2 coming in, and this is then getting converted into this ethanol. We have put here the table so you can see that how these systems are taking place. And with in situ operando IR spectroscopy, we were able to show how stepwise you have the CO2 reduction and how you create this type of a new carbonyl stretch, slowly giving way to COH and CO single bond stretch frequencies. So you can really monitor them step by step in your reaction system when you are doing electrocatalysis. So, and this is the reaction pathway, as I said you. So basically it goes via the formyl pathway. So here you have the CHU minus, which forms this glyoxal, and this then produces here by several steps ethanol. And on the other hand, you have the HCHO or formaldehyde. Now this formaldehyde goes into methanol. So these are the ways in which you can get these products quite systematically, and you can have a control in these systems. But of course, one of the weaknesses of this work is, for example, we still get a little bit of hydrogen, because you get some reduction of the water system, so there is slight amount of hydrogen, which we don't like. You can do a modular modification, and that's what I will show you here. Instead of instead of cobalt, if you put manganese, then that is more oxidizing, and this will then give you acetic acid. So this was a nice work that was done again by Shomi, just with manganese, and then we were able to get clear systems. And what I would like to tell you, if you are doing electrochemistry and if you want to know whether your reaction is happening or not, what you need to do, you need to do it under argon and run an LSV. And from the LSV, you can see if there is a difference, then you know that there is some reaction going on in the system. And that's what is important to keep in mind. So this is for the quick run. So you do a run, you don't even need to run a CV, you do the LSV, and then if you see a difference, you know for sure that you have a reaction going on in your system. That is the first way by which we test it in our lab. And then you can do mass spec, then you can do control potential electrolysis to see the stable catalytic current or electrolytic current, and then do more and more systematic work. But the first scanning or the first check is via this type of LSV systems. And what we are trying to do, and I have shown it but not here, in the last class I have shown now ED has already achieved this C3 formation. So, and we are waiting or we are working now for C4 and for higher types of species. Now very quickly, I will just show you that how you can do compartmentalization and do the reaction in two compartments. So what happens there is we made these soft-oxometalates, and then we put in carbon dioxide, and we were able to show that you have carbon dioxide reduction within the cavity and you have carbon dioxide reduction outside the cavity. So you can have both, and we were able to show that within the cavity you have different kinds of reactions as compared with the without or outside the cavity, and you will see different kinds of things. So I'm not showing you, so this is just the different types of characterization which we have done. The mechanism is also similar. At the two bandages you have this oxidation and reduction, but what is interesting is this one here. So in the internal cavity you see that as you increase the concentration, it goes up. That means you have the situation where you have larger cavity, larger and larger amount of formic acid is produced. But then you have the external cavity whereas the size goes up, your product goes down, and this is very typical. That means when you reduce the size, your product goes up. This is the basic principle of nanocatalysis, where you know that if you reduce the size, you have more and more active sites, and that's where you have more active catalyst. And we were very happy to see this effect in this type of system. So this was a work which was done by Oshi, who is now in Germany working as a postdoc. So with this, I hope that I have been able to convince you the reaction, so basically the partitioning of the reaction media, and how with partitioning of the reaction media, you are able to do reaction modularly inside the cavity and outside the cavity, and you can show that inside the cavity you have the effect of nanocatalysis, and outside the cavity you have the other effect. So I hope that with this we come to the conclusion. So what I have shown you is the framework of these SOMs, where you can do partition, reaction, motion, and harvesting the motion by assembly and disassembly. And now we are also able to create reactions to harvest energy. So with this, I conclude, and I'll be happy to answer your questions now or later, whenever you have. Thank you. And these are some journals where I serve the editorial boards. If you have nice work, please do send it over to this journal. It has now picking up with the impact factor, and of course in frontiers in chemistry and chemistry Africa. So thank you.